The students, today's class we'll start off with cone clutches. This is in continuation with module 4, which is including clutches and brakes, clutches and brakes. So in clutches, we are seeing only the friction type clutches. So under those friction type clutches, we have two more categories, which are disc and cone clutch. There are a variety of categories, but we are going to touch upon only these two categories as they are commonly used and pretty easy to understand and assimilate. So we have already completed the plate clutches, that is including single and multi-plate clutches. So this is the second variety of friction clutches, this is the cone clutch. The cone clutch works on a similar principle as the plate clutch, but here what is the advantage of this is it transmits the same amount of for the same amount of power transmitted. Now this cone clutch is more smaller in size, meaning it is more compact. Okay, it is packed in a smaller state because this wedge angle here, no? So this provides a more surface area for coverage. For the same surface area, you have to cover a bigger diameter in case of plate clutch. So if you just flatten this angle out now, so what happens is you'll get a bigger diameter of clutch if you use a plate clutch. So that's the advantage. For the same surface area, you have a smaller dimension here. So therefore, it is a little bit compact. And whenever it comes to engaging and disengaging, right? So this is easier and faster to disengage and engage because of this wedge action. Okay, so you have a wedge here, and where the friction material, you can see the black, which is bonded onto the inner core. Okay, so whenever it's easy to engage. So this is a spline shaft here. When the spring is actuated, you actuate the lever, it moves backward and forward, and this here is the driving shaft, which is connected to the flywheel. It's similar in operation to the plate clutch. So whenever it has an axial movement, it engages quicker, and torque transmitted is uh, equal. If for the equal amount of torque transmitted, you have a more amount of force, more amount of compactness you have in this kind of cone clutch. Right? So that's the advantage of a cone clutch. The design procedure is more or less same with some minor changes. We'll check it out next. So before we go to the design procedure, we'll just see the force analysis. So this is the diagram given in your data handbook. So there is not much of a derivation over here, just some analysis of forces and how what all forces do we consider over here. So if you assume a small elemental area in this cone, so this part, okay, the conical part is what we are worried more about, and this is what we will be designing. Suppose you have two diameters d1, d2, and you have the mean diameter dm, right? So take a small elemental area over here, and if you check out the forces acting, so have Fn, which is the normal force which is acting on this surface here, the conical wedge surface. When there is a normal force acting, it resolve this into three components. One is Fa, which is axial, is being applied, and Fr, which is radial, and one more force it cannot be seen, it is perpendicular to your diagram, that is perpendicular to the screen, that is the tangential force. So this force is a three-dimensional nature because of the conical nature of this uh, clutch here. So you have three forces where two of them are in majority. So what you will say is Fa, which is required to actuate this particular cone, and Ft, that is a tangential force. It is not seen here, but it is perpendicular from this point outside, coming outside from your screen, right, respectively. So that these two forces are determined as prime according to vast theory. So we'll find out Fa and Ft, that is tangential. So these are the two formulae which will be defined to know that Fa and Ft, the axial force and the tangential force in your data handbook 11.10a and b. So this can be seen easily from the geometry here. The alpha is nothing but the half cone angle. Okay, so this alpha angle is usually kept between 12.5 and 15 degrees. The optimal angle of cone, if you ask me, is around 12.5 degrees. So most commonly used. Okay. So mu, I think you know what mu is. This is coefficient of friction, and times the normal force will give you the tangential force, and that's it. So these two are the principal forces which we'll be finding in terms of forces. Coming to the design procedure. So as usual, we'll find what is the torque required to transmit. In case of the cone clutch also, the first step remains the same as the plate clutch. You have the power 2.T over 60. So N, again M has changed. You can keep it M or MT or T. So it doesn't matter. MT and T both are same. This is N. This is not M. This is N. N is the RPM here. And diameter of shaft. Diameter of shaft is the one which transmitted connects to the transmission shaft or the gearbox and stuff. So that diameter is the cube root of 16 T by pi cube. So these both are not in the data handbook. You are required to memorize these both formulas. Is there in the data handbook, but you have to search a lot. So better, most frequently used formula you can by heart. Then we'll find mean diameter if not given. So this is first type. I forgot to tell you, this is type 1. The first type is when mean diameter is not given. Okay, if mean diameter is given, only one step you need to see. The third step you need to see. So most commonly you'll encounter this type of a problem where mean diameter is not given for the cone. So in that case, you are required to assume this ratio here. So dm by b. B is nothing but the face width of the wedge as seen in the diagram. So this is 4.5 to 8. You assume anywhere in between this value and proceed further. And find the axial force using the mean diameter, face width, P is for pressure, and sine alpha. Alpha, as I told you, it will be optimally between 12.5 degree. And based on the data handbook values, we have given either leather faced or wood faced. So this is 13.4 table. Depending on the opposing and bearing material, we are required to assume the pressure. So the small p which we saw will come here. Okay, and also this alpha. Alpha is faced with leather or faced with wood. Wood in the sense sometimes cork is used. So leather, cork, and asbestos. These are the three most common materials which we used for the friction lining. So here in this set handbook, you have two types, that is leather and wood. Asbestos is not given. So maybe only these both are in use, right? So this is in page number 259. You can refer to this. Then step 5 is torque capacity. So this is for exclusive for cone clutch, that is given as MT. Torque transmitted for a cone clutch 13.10, right? And last step, equating both, same as that of the plate clutch. Capacity is what we get from step 5 should be greater than or equal to what we get from step 2. Okay, at least you should have this. And finally, we find the dimensions d1 and d2 using these equations. This step is just finding the axial force necessary. Fa, if asked in the question, the axial force required to find, required to engage the cone clutch. So then we use these two equations, combination of these two equations necessary to engage the clutch. So Fa we would already got, and we'll find out Fa dash. So in type 2, if the diameter is not given, just skip step 3 and we can directly go for step 4 and find all the other required values. We'll start off with the numerical. Okay, let's check out the first problem. Check out this first problem. A cone clutch transmits 7.5 kilowatt at 900 rpm, and the phase angle is 12.5 degrees. The cone face is lined with leather, and normal pressure between the faces not to exceed zero 0.9 meganewton per meter square. So let's note down this data one by one.